Somewhere in a lab cooled colder than deep space, a tiny chip just did something that took scientists by surprise, and within days the internet had turned it into a headline that said, "Google's quantum chip had replaced silicon." That headline spread fast. It got shared, reposted, and turned into thumbnail after thumbnail promising that the age of silicon computing was already over. But before you believe that silicon is dead and quantum chips are about to take over your phone, your laptop, and every data center on the planet, you need to hear the real story, because what actually happened is stranger, slower, and honestly more interesting than the headline lets on. Let's start with the chip everyone is talking about. It's called Willow. It comes from Google's quantum AI division. Willow is not a phone processor. It's not something that will ever sit inside a laptop the way an Intel or Apple chip does. Willow is a quantum processor, built using superconducting circuits that have to be cooled to temperatures colder than outer space just to function at all. When Google unveiled Willow, they weren't claiming it would replace the silicon chips inside your everyday devices. They were announcing a breakthrough in something quantum scientists have been chasing for almost 3 decades, a problem called error correction. To understand why that matters, you need to understand what makes quantum computers so different from the computer you're using right now. Every device you own, from your phone to your smart fridge, runs on bits. A bit is either a 0 or a 1. That's it. Every photo, every video, every calculation your phone has ever done comes down to enormous strings of zeros and ones flipping on and off inside silicon transistors. It's an incredibly reliable system. It's the reason silicon has ruled computing for more than half a century. Quantum computers throw that entire system out the window. Instead of bits, they use qubits. And qubits don't have to be just a 0 or just a 1. Thanks to a strange property of quantum mechanics called superposition, a qubit can exist as a mix of both states at the same time. It sounds like science fiction, but it's very real physics, and it means a quantum computer doesn't process information one step at a time the way your laptop does. It can explore a staggering number of possibilities simultaneously. Add in another quantum property called entanglement, where qubits become linked so that the state of one instantly affects another, and you get a machine that, for certain types of problems, can outperform every classical supercomputer on Earth combined. That sounds incredible, and it is, but qubits have one massive weakness. They're fragile, unbelievably fragile. The tiniest vibration, the smallest change in temperature, even stray electromagnetic noise from a wall outlet somewhere in the building can cause a qubit to lose its quantum state. Scientists call this decoherence, and it has been the single biggest obstacle standing between quantum computers as laboratory curiosities and quantum computers as genuinely useful machines. For decades, adding more qubits to a quantum processor didn't just add more computing power, it also added more chances for something to go wrong. More qubits meant more errors, and more errors meant the whole calculation could fall apart before it even finished. This is the wall Google's Willow chip smashed through, at least in a meaningful way. Willow demonstrated something called below-threshold error correction. In plain language, that means that when Google added more qubits to the system, the error rate went down instead of up. That's the opposite of what used to happen. For nearly 30 years, researchers in this field treated that outcome as the finish line for one of quantum computing's oldest and hardest problems. Willow crossed that line. And to make headlines even bigger, Google ran a benchmark test on Willow that took under 5 minutes to complete. That exact same calculation, if you tried to run it on one of today's fastest supercomputers, would take 10 septillion years. That's a 1 followed by 25 zeros. It's a number so large it makes the age of the entire universe look tiny by comparison. Now here's where you need to pay close attention, because this is exactly where the confusion started. Willow did not replace silicon. Willow doesn't even try to do the kinds of things silicon chips do. Willow can't run your apps, browse the internet, edit a video, or power a spreadsheet. What Willow is extremely good at is a very specific category of calculation, the kind that involves simulating quantum systems, exploring massive combinations of variables, or solving optimization problems that would take a classical computer longer than the universe has existed to work through. Silicon chips, meanwhile, remain unbeatable at the everyday tasks that make up almost everything we do with computers. Quantum and classical computing aren't rivals fighting for the same throne. They're built to solve completely different kinds of problems. And for the vast majority of what computers do today, silicon isn't going anywhere. So if Willow isn't replacing silicon, where did this whole idea come from? That brings us to a separate and genuinely fascinating breakthrough, this one from Princeton University, announced in partnership with funding support from Google Quantum AI. And ironically, this story is almost the opposite of what the viral headlines claimed. Instead of quantum chips replacing silicon, Princeton's researchers actually brought silicon back into the picture in a way nobody expected. Here's the background. The basic building block of most of today's leading quantum computers, including Google's, is something called a transmon qubit. Think of it as a tiny superconducting circuit that has to be manufactured with extraordinary precision. For years, the industry standard was to build these transmon qubits on a substrate made of sapphire. Sapphire worked well enough, but it had a hidden cost. It was quietly leaking energy out of the qubits, shortening how long they could hold their fragile quantum state before decoherence set in. And that lifespan, known as coherence time, is one of the most critical measurements in quantum computing. The longer a qubit can hold its state, the more calculations you can perform before the information falls apart. A team at Princeton, led by Andrew Huck, the university's Dean of Engineering, and Nathalie de Leon, co-director of Princeton's Quantum Initiative, decided to attack this problem from two completely different angles at once. First, they swapped out the metal typically used in these qubit circuits for tantalum, a material known for holding on to energy far better than the alternatives. Second, and this is the twist nobody saw coming, they replaced the sapphire substrate with high-quality silicon. Yes, silicon, the exact material the headlines claimed was being replaced. In reality, silicon was making a comeback, not an exit. Getting tantalum to grow properly on top of silicon wasn't easy. The two materials have very different physical properties, and past attempts by other labs had struggled to make the combination work reliably. Two researchers on the team, graduate student Matthew Bland and postdoctoral researcher Faranak Bahrami, spent enormous efforts solving the technical challenges standing in the way. When they finally cracked it, the results were staggering. The new qubit held its quantum information intact for more than 1 millisecond. That might sound like an impossibly short amount of time to you and me, but in the world of quantum computing, 1 millisecond is an eternity. It's roughly 3 times longer than the best coherence time ever recorded in a laboratory setting, and nearly 15 times longer than what today's best industrial quantum processors typically achieve. To put that number in perspective, Andrew Huck said that swapping the current industry standard qubit for Princeton's tantalum on silicon design in a hypothetical 1,000 qubit quantum computer wouldn't just make it a little bit better, because the benefits scale exponentially as you add more qubits. That upgrade could make the machine perform roughly 1 billion times better. 1 billion. Not 15 times, not 1,000 times, a billion. That's the kind of number that stops physicists in their tracks. And it's very likely the real source of the excitement that eventually got twisted into misleading headlines about silicon being replaced. Michel Devoré, the chief scientist for hardware at Google Quantum AI and a recipient of the 2025 Nobel Prize in Physics, didn't hold back his praise for the work. He described the long struggle to extend the lifespan of quantum circuits as something that had become a graveyard of ideas for many physicists over the years. Countless approaches had been tried and had failed to produce a meaningful breakthrough. He credited Nathalie de Leon specifically with having the persistence to pursue an unconventional strategy and actually make it succeed, where so many others had given up. Hawke himself called the Princeton chip a major breakthrough on the path toward enabling useful quantum computing, and he wasn't shy about calling it the largest single leap forward in the field's history in more than a decade. There's another benefit to this new design that doesn't get nearly as much attention as the coherence time numbers, but might matter just as much in the long run. Silicon isn't just a better performer in this context, it's also cheaper, more widely available, and dramatically easier to manufacture at scale than sapphire. The global semiconductor industry has spent more than half a century perfecting the art of working with silicon. Factories, tools, expertise, and supply chains built around silicon already exist all over the world. That means a quantum chip design built around high-quality silicon isn't just a scientific curiosity sitting in a university lab. It's something that could realistically be manufactured, using infrastructure the tech industry already has in place. De Leon pointed out that their tantalum silicon chip doesn't just outperform existing designs, it's also considerably easier to mass produce, which is exactly the kind of practical advantage that could accelerate the timeline for quantum computers, moving from research labs into real-world use. Now, if that story wasn't enough to keep track of, there's a third piece of this puzzle that adds even more nuance and comes from a completely different company altogether. A quantum computing company called SQC, led by physicist Michelle Simmons, took an entirely different route toward building a quantum processor, one that leans on silicon in a much more literal and direct way than either Google or Princeton's approach. Instead of using superconducting circuits sitting on top of a substrate, SQC built what they call an atomic quantum processor, using an architecture they named 1415, a reference to the atomic numbers of the elements involved. Their method involves placing individual phosphorus atoms directly inside pure silicon wafers, essentially embedding the quantum bits atom by atom into the silicon itself. The results SQC reported were remarkable in their own right. Their system achieved fidelity rates as high as 99.99%, which is an extraordinarily high level of accuracy for a quantum system. High fidelity matters enormously in quantum computing because every single error a qubit makes has the potential to snowball into a much larger error as calculations progress. SQC's design, built using 9 nuclear qubits and 2 atomic qubits, marked what researchers described as the first demonstration of atomic, silicon-based quantum computing operating across separate clusters. According to Michelle Simmons, this atomic-level precision means the system experiences far fewer of the more disruptive types of errors that plague other quantum architectures, which in turn means the amount of extra computing overhead needed just to correct those errors ends up being much smaller than in competing designs. Their research was published in the scientific journal Nature, giving it the kind of rigorous peer review that separates genuine scientific progress from hype. So now you can see exactly how a nuanced, layered, genuinely exciting series of scientific developments got flattened down into a single misleading headline. Google's Willow chip achieved a historic breakthrough in error correction, a completely different kind of achievement from replacing silicon. Princeton's team achieved a historic breakthrough in qubit lifespan by combining tantalum with silicon, which, if anything, brought silicon further into quantum computing rather than pushing it out. And SQC achieved a historic breakthrough in fidelity by embedding quantum bits directly into silicon atoms. None of these breakthroughs involved quantum chips replacing silicon in your phone, your laptop, or anywhere close to the devices most people use every single day. It's worth pausing here to talk about why this kind of misunderstanding happens so often with quantum computing news specifically. Quantum mechanics is genuinely one of the strangest and most counterintuitive branches of physics ever discovered. Concepts like superposition and entanglement don't have a clean, everyday equivalent that makes intuitive sense to most people. When a real scientific paper describes a breakthrough, using precise, careful language, that nuance often gets lost the moment it passes through a chain of secondhand summaries, social media posts, and clickbait headlines competing for attention. A phrase like tantalum grown on a silicon substrate can quietly transform into replaced silicon by the time it's gone through 3 or 4 rounds of retelling, and by the time it reaches your feed, the science has been stretched into something the original researchers never actually claimed. This matters because it shapes how the public understands the pace of technological change. When people hear that quantum chips have replaced silicon, it creates an expectation that quantum computers are about to show up in consumer products any day now. The reality is far more gradual, and honestly, far more grounded. Quantum. Computers today are still enormous, delicate machines that require dilution, refrigerators to cool their qubits down to temperatures a fraction of a degree above absolute zero. They require specialized facilities, teams of physicists, and carefully controlled environments just to keep the qubit stable long enough to run a calculation. None of that is compatible with putting a quantum chip into a smartphone anytime in the foreseeable future. What is realistic, and what these breakthroughs genuinely point toward, is a future where quantum computers become useful tools for specific, narrow categories of problems long before they ever become general-purpose replacements for the silicon chips inside everyday devices. Drug discovery is one of the most frequently mentioned applications because simulating how complex molecules interact with the human body is exactly the kind of problem that overwhelms classical computers but plays to the natural strengths of a quantum machine. Materials science is another promising area. Since designing new materials, like more efficient batteries for electric vehicles or better components for fusion energy research, often requires modeling quantum-level interactions that classical computers can only approximate. Optimization problems in logistics, finance, and artificial intelligence training also stand to benefit because these often involve searching through an almost incomprehensibly large number of possible combinations to find the best solution, which is precisely the kind of task quantum computers are built to handle. Financial institutions are also watching closely, since portfolio optimization and risk modeling involve searching through combinations of variables so vast that classical computers can only ever approximate the best answer, whereas a mature quantum system could, in theory, search that space far more directly. None of these applications require quantum computers to replace the silicon chip in your phone. Instead, the future many researchers are actually working toward looks more like a hybrid system, where classical silicon computers continue to run the vast majority of everyday tasks, while quantum processors get called upon for very specific, computationally extreme problems that classical machines simply cannot solve in a reasonable amount of time. In this model, quantum computers become a specialized tool sitting alongside classical computing, not a replacement for it. Google's own researchers have described this vision directly, explaining that many of the most promising future applications for quantum computing, from discovering new medicines to designing next-generation energy technologies, simply won't be feasible on classical computers at all. They're not framing this as quantum replacing classical computing. They're framing it as quantum computing unlocking an entirely new category of problems that classical machines were never capable of solving in the first place. It's also worth mentioning that Google isn't the only major player pushing quantum computing forward, and that competition is part of why progress has been accelerating. IBM has its own long-running quantum computing program built around superconducting qubits, similar in basic principle to Google's approach, but developed independently, with its own roadmap toward larger and more reliable quantum processors. Other companies have taken fundamentally different physical approaches altogether. PsiQuantum, for example, has focused on developing qubits made from particles of light itself, a photonic approach to quantum computing that comes with its own unique set of advantages and engineering challenges compared to superconducting circuits. IonQ has taken yet another path, working with trapped ion qubits, where individual atoms are captured and held in place using precisely controlled lasers, sometimes described as a kind of laser tweezer system. Each of these approaches, superconducting circuits, photonic qubits, trapped ions, and the silicon-based atomic qubits pursued by companies like SQC, represents a genuinely different bet on which physical system will ultimately scale up most successfully into a large, reliable, error-corrected quantum computer. Nobody in the field has definitively declared one approach the winner yet, and it's entirely possible that different architectures will end up being better suited for different types of problems, rather than one single design dominating the entire industry the way silicon transistors came to dominate classical computing. Circling back to where we started, it's worth being clear about exactly what changed and what didn't. Silicon is not dead. Silicon is not being phased out. The chip inside your phone right now, and the chip that will be inside your next phone, and very likely the phone after that, will still be built using silicon transistors, the same basic technology that has powered the digital revolution for more than 50 years. What did happen is a series of genuinely remarkable scientific advances that are slowly, carefully, and rigorously pushing quantum computing closer to practical usefulness. Google's Willow chip proved that adding more qubits can reduce errors instead of increasing them, cracking open a problem the field had struggled with for decades. Princeton's tantalum on silicon qubit dramatically extended how long a qubit can hold its fragile quantum state, and did it in a way that could realistically be manufactured at scale using silicon-based infrastructure the industry already has. And SQC's atomic quantum processor demonstrated extraordinarily high fidelity by embedding qubits directly into silicon at the atomic level. Put those three threads together and you get a much more accurate and honestly much more compelling story than any single misleading headline could capture. This isn't a story about silicon losing to quantum computing. It's a story about scientists finding new and creative ways to combine the best qualities of both worlds, using tried and tested materials like silicon in entirely new configurations to solve problems that have haunted quantum physicists for nearly 3 decades. It's a story about persistence, about researchers spending years chasing ideas that other people in the field had already given up on and quietly labeled as dead ends. It's a story about incremental, hard-won progress rather than overnight revolutions, even when the headlines make it sound like everything changed in an instant. If there's one thing worth remembering after all of this, it's that real scientific progress rarely looks like the dramatic, world-changing moment social media makes it out to be. It looks like a graduate student and a postdoctoral researcher spending countless hours in a lab trying to grow one specific metal onto one specific substrate, failing repeatedly, adjusting their approach, and eventually succeeding in a way that quietly moves an entire field forward by years. It looks like a team measuring coherence times in fractions of milliseconds and treating a threefold improvement as one of the biggest breakthroughs of the decade. It looks like careful, peer-reviewed publication in journals like Nature, rather than a single flashy announcement designed purely to go viral. It's also worth stepping back and appreciating just how long this journey has already been, because none of this happened overnight, no matter how the headlines frame it. The idea of a quantum computer isn't new. Physicist Richard Feynman first proposed the concept back in the early 1980s, arguing that if you wanted to simulate nature accurately, you'd eventually need a computer that operated on quantum principles itself, because classical computers simply couldn't keep up with the complexity of quantum systems. For decades after that, quantum computing remained almost entirely theoretical, a fascinating idea confined to physics papers and academic conferences with no real hardware capable of demonstrating any of it. It took until the early 2000s for researchers to start building small experimental qubits in laboratories, and even then, those early qubits could barely hold their quantum state for a few nanoseconds before collapsing. Getting from those first fragile nanosecond qubits to Princeton's millisecond scale qubit today represents literally millions of times improvement in stability, achieved gradually across 2.5 decades of painstaking research, false starts, and slow, hard-won progress. Understanding that timeline helps put the current wave of announcements into perspective. When Google first demonstrated what it called quantum supremacy back in 2019, showing that its quantum processor could complete a specific calculation faster than any classical supercomputer, some headlines back then also declared that classical computing's days were numbered. That obviously didn't happen. What actually happened is that quantum supremacy demonstrations, while genuinely impressive engineering feats, were narrowly designed benchmark tests, rather than proof that quantum computers were ready to take over general-purpose computing. The same pattern is playing out again now with Willow, with Princeton's tantalum silicon qubit, and with SQC's atomic processor. Each of these represents real, measurable, peer-reviewed progress, but each one is also a single piece of an enormously complex puzzle that still needs many more pieces before quantum computing becomes something ordinary people interact with directly. One of the biggest remaining pieces of that puzzle is scale. Willow currently operates with just over 100 qubits. Experts in the field generally agree that truly transformative, fault-tolerant quantum computers, the kind capable of reliably solving problems like large-scale drug simulation or breaking modern encryption, will likely need somewhere in the range of thousands to millions of stable, error-corrected qubits working together. Going from a few hundred qubits to that scale isn't simply a matter of building more of the same. Every additional qubit introduces new engineering challenges, new sources of potential error, and new demands on the surrounding infrastructure needed to keep everything cold, stable, and precisely controlled. This is exactly why breakthroughs like Princeton's tantalum on silicon design matter so much, because a design that's easier to manufacture at scale using existing silicon industry infrastructure could meaningfully shorten the path toward those thousands or millions of qubits, compared to more exotic and harder to produce alternatives. There's also the question of cost, which rarely gets mentioned in viral headlines, but plays an enormous role in how quickly any of this technology becomes widely accessible. Building and maintaining a quantum computer today requires dilution refrigerators that can cost millions of dollars, specialized cleanroom facilities, and teams of highly trained physicists and engineers to operate and calibrate the system. That kind of investment is currently only within reach of major technology companies, well-funded research universities, and government-backed research centers. The Princeton research itself was primarily funded through the U.S. Department of Energy's National Quantum Information Science Research Centers, along with a specialized research center called the Co-Design Center for Quantum Advantage, underscoring just how much large-scale public investment is still required to push this field forward. Bringing costs down enough for quantum computing to become commercially widespread, the way silicon chips eventually became cheap enough to put a computer in every home, will likely take many more years of parallel progress in manufacturing, materials science, and engineering, not just in qubit design alone. None of this is meant to diminish how exciting these breakthroughs genuinely are. It's meant to give you a realistic, grounded understanding of where things actually stand, rather than the exaggerated version designed purely to generate clicks and views. The scientists behind Willow, behind Princeton's tantalum silicon qubit, and behind SQC's atomic processor aren't claiming to have replaced silicon, and they're not claiming quantum computers are about to show up in your pocket. What they are claiming, carefully and specifically, is that some of the hardest, most stubborn problems standing between quantum computing and practical usefulness are finally starting to yield to persistent, creative research. That's a genuinely big deal. It just doesn't need exaggeration to be a big deal. Looking ahead, most researchers in the field are cautious about putting exact dates on when quantum computers will start solving problems with genuine, everyday commercial value. But there are some rough milestones worth watching for. The next major checkpoint isn't a headline about replacing silicon, it's steady progress on scaling up qubit counts while keeping error rates low, something Google has already outlined as part of its own long-term roadmap toward what it calls a useful, large-scale quantum computer. Watch for announcements about 1,000-qubit systems maintaining low error rates. Watch for manufacturing partnerships that bring silicon-compatible qubit designs like Princeton's out of the lab and into pilot production lines. And watch for the first genuinely practical applications in narrow fields like drug discovery or material simulation, rather than sweeping claims about quantum computers taking over everyday tasks. Those milestones will tell you far more about real progress than any single viral headline ever could. So the next time you see a headline claiming some new chip has replaced silicon overnight, or that quantum computers are about to take over your everyday devices, take a moment to look a little closer. More often than not, what you'll find underneath the exaggeration is something even more interesting than the headline suggested. A genuine, hard-earned scientific achievement that's slowly reshaping what future computers will be capable of, one careful, patient breakthrough at a time. Silicon isn't disappearing. If anything, based on what Princeton and SQC have both shown us, silicon might end up playing an even bigger role in the future of quantum computing than anyone originally expected. Real progress in this field looks less like a sudden revolution and more like decades of patient, incremental work finally starting to compound. One improved coherence time, one lower error rate, one successfully manufactured chip at a time. And that, in the end, is a far more fascinating story than the one the clickbait headlines were trying to sell you.